Now, when we're dealing with exergy and exergy analysis, one thing that we do need to consider is the amount of work that we are doing on the surroundings. So exergy itself considers performance with respect to a dead state Now, what we need to do is, given that we're considering the performance of a system with respect to the dead state, if we are doing work on the surroundings, that would be the case where we have a control volume that is changing with time throughout our process, and it would be one of either expanding or contracting. If it's contracting, the surroundings is doing work on our control volume. But let's assume that our control volume is expanding. Well, in that case, we are doing work on the surroundings, and the work that we perform on the surroundings can be quantified as the dead state pressure multiplied by the volume change. And so what we need to do when we're evaluating the amount of useful work that a system can do, we need to take the work that we're doing on the surroundings into account. So the amount of useful work that we get, and we'll denote that with a W subscript U, is equal to the work minus the work that we do on the surroundings. And by substituting in the quantity that we said was for the work on the surroundings, the W here is the actual work being performed. So that is something that we have to be careful about. If we have a control volume that is changing volume, we need to take into account the fact that we may be doing work on the surroundings. And there are two more terms, or I guess terms would be the best, that we should think about. One is reversible work, and we will talk about these. Reversible work is defined as being the maximum amount of useful work that can be produced. So that is what reversible work refers to. And it makes sense. It would just be the maximum amount of work that you could produce if you had no irreversibilities in your system. So when we looked at the example of the Carnot heat engine a moment ago for the example problem, and we had the source at 1500 Kelvin, the amount of useful work coming out, or reversible work, was that from the Carnot efficiency. Another term that you'll hear discussed when we talk about exergy and exergy analysis is the term irreversibility. And what this is, it's basically exergy that is lost or destroyed through our process. So we want to minimize irreversibility as engineers. These are losses in our system. And irreversibility would be defined in two ways depending on if we are looking at a system that is producing work or a system that we are doing work on it. And so taking a look at the first, where we have a system that produces work, irreversibility would be reversible work out minus useful work out. And if you have irreversibilities, what will happen is reversible work out is your ideal state, and it will always be larger than the actual or useful work that you get out of your system. And consequently, irreversibility in this will always be a positive number. Or you can have irreversibility expressed as useful work in minus reversible work in. And reversible work in on a device that you're doing work on, such as a pump or a compressor, is always going to be less than the useful work that you're actually putting in. And consequently, this will always be a positive as well. So always positive and always positive. And this is work producing. And this is work in, or work, we'll call it input. So that would be something like a pump or a compressor, and work producing would be a turbine. So what this is, it's a quantification of exergy lost or destroyed. Sometimes you'll hear the term exergy destruction, and what we're referring to are the irreversibilities that exist within our system. And our job as engineers is to minimize those irreversibilities. So those are a couple of concepts that we'll be discussing when we continue on through exergy analysis.